bring Sarah's quiz back. I'll bring it back in a minute. Anyone who finishes it is welcome to show your solution on the board. want to show you work here on the board? Yeah, one of you can take care. Thank you. You want to show your work here? Next time. Oh, you want to do it? No. Yeah.
I don't know the value of cosine at a certain point.
Yeah. Do you want to just show me how? Maybe I can walk through. You can guide me.
Okay.
Yeah.
So the first step is to find the derivative of fx.
So you compute f prime x. I will give you
2 cosine x minus 1. And so then you have to find,
pretty one number. So what are at x? That's the big question. So cosine equals 1/2. What you really need is the picture. Well, first of all, cosine equals 1/2. There is a special angle. Which one is that?
60.
This is 60 degrees. That one, I think a lot of us know that. So x, by the way, you want to say x equals pi over 3 rather than 60 degrees, okay? Because this here, x should be pi over 3 rather than 60. Okay, so you know there's one angle here, which is pi over 3. Now here's something you really need to know. In order for cosine to remain to be 1/2, there should be some other angle, which also gives you 1/2. Which one is that? I know it's hard to say. Is it here in the second quadrant, or here in the fourth quadrant, or where? The second quadrant? Do we agree? Okay, let's remember the sign of cosine. Cosine is positive here. Is it positive here? It's negative because it's x over r. So here is negative. It cannot be equal to 1/2. Here it is a negative. Here it is a positive. So these two would have the same value, really. Okay. So once you have pi over 3, there's another one here. Which one is that? It would be symmetric. So if you go pi over 3 here, this should also be pi over 3. Okay. And because we are looking at within this range, so that means, let's see, pi minus pi is here. And you go around it, you hit once. Okay, then here's another one. That's 0, and then pi, and then 2 pi. So really, there should be 3 solutions. You see that? Because you're ranging from minus pi to 2 pi. So let me write down the 3 solutions. X should be equals to 1 is minus pi over 3. And the next one is pi over 3. And the last one is you rotate until you're almost 2 pi. So that will be 2 pi minus pi over 3. Right? So 2 pi minus pi over 3, which is just that's 5 pi over 3, right? 5 pi over 3. Yeah, that's right. 5 pi over 3 plus pi over 3 is 2 pi. So we got those 3 numbers. And then you just have to make a table including those 3 numbers plus the 2 endpoints. So you make a table like this, x and the fx. And you put those 3 critical numbers here, minus pi over 3, pi over 3, 5 pi over 3. Those are the 3 critical numbers. And then you include the 2 endpoints, which are minus pi and 2 pi. Okay, then you just plug in the value for each one of them. I guess there's a lot of tricks that cause the headache here. So now you have to know what is the sign of negative pi over 3. What is that? The sign is going to be negative here. You should remember the sign is positive, positive, negative, negative. Okay? So sine positive pi over 3, that's square root of 3 over 2. Because we're dealing with a negative, so negative square root of 3 over 2, 2 and 2 cancel. So this is going to be negative square root of 3, right? Minus negative pi over 3, so that becomes a plus pi over 3. Any questions on that? That's what I did. Yes?
Question, where did you get the negative pi over 3?
Where did I get this to begin with? Yeah. So basically we are solving for that equation. Let me just do it on the side here. We try to solve for cosine x equals 1/2. Okay? You got an easy solution first, which is x equals pi over 3. That one is relatively easy, and it's right here in the first quadrant. But then remember, cosine is positive here, negative here, and negative here. Okay, so there should be another solution down here, which is symmetrical to this one. So I'm going to draw that one. That one, if you draw it, it's going to be just, it's just like this. This is the other one. Okay? And it's totally symmetric, meaning that if this is 60 degrees, this should also be 60 degrees. Pi over 3. And therefore, this angle is a negative pi over 3. That's how I got this one. Okay? It's the one that you start from the x-axis rotate clockwise. So that's x equals negative pi over 3. That's the second one. And then there's a third one, which is you just go around. So, this is the one, this is another one. The third one is you go around, you go around it here. It's slightly less than that. It's the same angle, but it's viewed as you go around one more time. So it's 2 pi minus pi over 3. That's the third one. Yes?
How did you get over 3?
Well, because I'm looking at the angles from here to here. In general, if you want in general, let me just finish this one first. The third one is 2 pi minus pi over 3, which is 5 pi over 3. In general, if you want to write all the solutions from minus infinity to plus infinity, what would those be? Well, these are the two basic ones, 1 and 2. To get all of them, you just have to add 2n pi. So in general, the solution would be x equals to 2n pi, where n is integer, plus or minus pi over 3. Okay? As you run through all integers n, you will find out exactly 3 of them will fall into this range. And the rest of them will be outside. Okay? All right, this is computationally less friendly than I expected, but you have to deal with that. So let's do it. Pi over 3, plugging pi over 3, square root of 3 over 2, cancel with the 2. So square root of 3 here, and then minus pi over 3, that's the second one. All right? And then 5 pi over 3, you substitute the 5 pi over 3 here. Remember, 5 pi over 3 is down here. Okay, so this part will give you negative square root of 3, and then minus 5 pi over 3. All right? And then you do the end points. Well, minus pi and 2 pi. Minus pi, that gives you 0, minus pi, so it's a positive pi, right? And 2 pi gives you 0 here, negative 2 pi. So let's see, which one looks to be big, which one looks to be small. Is that clear? So pi over 3 is roughly 1 point something, 1.0 something. This one is a negative 1.7. So this is a negative number. This is just the opposite of that. This is very negative. This is very negative. I would say this is the biggest one. Yeah, is that clear to us?
Yeah.
So pi is the absolute maximum. All right. And maybe this is the absolute minimum. Let's see. I think the only thing that can compete would be this one between those two. So how do we compare? Minus 2 pi is exactly negative 5 pi over 3 minus pi over 3, right? Why do I do that? I'm trying to compare those two numbers. I'm trying to see which one is smaller. These two are equal. This part are equal, so it's a matter of comparing those two. Well, this is negative 1.7. This is negative 1.0 something. So this one is even more negative than this one. So I would say this is the absolute minimum. That's the conclusion that I made. Are we okay with that? Yes.
Why are negative pi over 3 and 5 pi over 3 like equivalent in regards to if you like look at the unit circle or the graph that you did to the right? They're both going.
Yeah,
the
they
same.
both end at this this line, right?
Yeah.
But they are regarded at a different angle because if you talk about negative pi over 3, that's obtained by rotating clockwise 60 degrees. That's how you get there.
Okay, so
Okay?
say if you did it right on the y-axis, it was pi over 2, and this is a different example. If it was pi over 2, you'd have to do pi over 2, negative pi over 2, and 3 pi over 2. Or both.
I mean, if you have a different problem.
Yeah.
Yeah,
you always have
those
to
three
do
would
negative.
be considered as different angles. Exactly. Let me just finish off. So minus pi over 3 is this. Now what is 5 pi over 3? It's this one. Okay?
Yeah, I was just making sure. Your other problem.
So I don't know if you have been to military training, but you know in the military they tell you to rotate like left or right, right? The left, I guess this is called left 90 degree, or turn right. How do you actually say that? And then turn back, right? There's one command called turning back, right?
Left, right,
So
about
did they actually tell you left or right? I don't know. Did they?
Yeah.
Anybody
I
has
understand what you're saying.
Do you see left back or right back?
I don't.
I don't really know.
Left face, right face, about face.
Left face,
Yup.
They're facing movement, so left face,
left.
no big.
Okay, so they are not quite the same, right? I mean, the endpoints are the same, but the process is different. So those two are not really the same. It actually becomes more clear when you look at the angles on the x-axis, right? So this is the x-axis, and then you go pixels. So this is 0, this is 2 pi, and then 4 pi. And the picture here, they're all the same. But once you stretch it out, they're different. So there is a difference. Okay. Let's say for this example. Questions? I feel like this is one of the more complicated examples because the trig function is involved. So take it as a good thing to review your algebra. So let me move to the new section. So last time we talked about section 3.1. Today we're going to talk about 3.2, possibly the next section. 3.2 is called mean value theorem. Okay. Slightly perhaps abstract for some of us, but it turns out to be extremely useful throughout this chapter and also later. So I'm going to state a simpler version of the mean value theorem. This one is called a Rolle's theorem. I think this the only theorem by Rowe who's I'm aware of. It's got his name under this theorem. So I'm going to state the theorem here. Fx is continuous on the closed interval AB and if it is differentiable on the open interval from A to B, then this is the condition for mean value theorem. So for Rowe's theorem, we have another condition, and FA equals to FB. Then there is a C somewhere in the middle. C inside the interval from A to B, such that f prime C equals to 0. Right? That's the statement. The condition looks a little bit scary because of all those statements. I mean, it seems like it's something really subtle. Continuous on the closed interval, differentiable on the open interval. The only difference here is the end point A and B. What's the big deal? Why you want to make those subtle differences? Fortunately, for most of the functions we deal with, they all satisfy that. I mean, all the functions, most of the functions we deal with, they are automatically differentiable. So you can take this as a statement that says f is a friendly function. It's a nice function. Okay, that's all it means. But if you want to be more subtle, that's the precise statement. And then you do want to f a equals b. That just means the starting point and the ending point are at the same level. Okay. Let's look at the picture and see why something like this has to be true. So suppose we have a nice looking function like this. X-axis and the y-axis. Fa equals fb. That means you start at this point and ending at this point. I just draw a random function. And let's see if it's true. Okay, draw a function. So for the picture that I draw, is there such a C? Such that f prime C equals 0?
Yeah.
Yes. Looks like the C is here, right? Okay. And you can draw another function. Fa, fb. And if you don't like the picture I draw, you draw another picture. Again, it looks like there is a C. Right? So, I mean, you can try to draw pictures by yourself. If anyone can draw a strange function for which f, there's no C, let us know, okay? You can try to draw something that the conclusion is not true, but you just cannot do it. So you can draw more complicated graph, like this is A, this is B, go up and down, several times. And it just gets worse. I mean, you get more and more C's if you try to make it more complicated, right? So, okay, so can we actually prove it? Actually, we are able to pretty much prove it. Let me just explain the idea of the proof rather than actually providing a full proof. So here is a sketch of the proof. Idea of the proof. Okay. So because it's continuous, I mean from the picture I draw, it looks like you can pretty much take C to be like a local, like an absolute max and absolute minimum. Something like that, right? And that pretty much proves it. I mean, so first of all, if it is because it's continuous, we learned that yesterday that as long as f is continuous on a closed interval, then there has to be some absolute maximum. It can be realized. So that was a statement I made yesterday, and I said it's not easy to prove. So you just have to believe me, I think. Yes. So f is continuous implies there is a absolute maximum. Close interval. Therefore, you can take a minimum if you want. Let me just take absolute maximum. And let's say, let's give it a name. We can just say FC. Let's call it FC. Well, the hope is that f prime c will be 0. Well, let's try to remember what else we learned. Yesterday, another thing we learned was that if you have a local maximum or local minimum, then c has to be a critical number. It means either f prime c equals 0 or f prime c does not exist, right? So it looks like either one, there are only those possibilities. So either f prime equals 0, for which case we're done. That's the conclusion. Or what else could be true? F prime c does not exist. How do you deal with that? Could that happen? Or you can actually draw a picture for which f prime c does not exist. Can you imagine a picture? This is the fa, this is the fb. There's some place where f prime does not exist. What would that picture be? What's that? Like an absolute value kind of function, right? Yeah. So you can draw something like this. And then you say, hey, this theorem is not true, right? There's no such prime c such that f prime c equals 0. Well, now look back here. Is that really, are we really saying the theorem is wrong? What's the problem with my example? It's not differentiable, right? Yeah. Remember this, it requires f is differentiable. So in a way, the picture that I draw is not a friendly function. Okay? It has to be smooth, really differentiable everywhere. So this case does not occur because it's not differentiable. Right? So it cannot happen because it's not differentiable. Since f must be differentiable by assumption. Okay? Now, are you saying we're done? We proved that? Well, you can say we're proved, but then look back here. Hey, we never used the fa equals fb, so what's going on here? Did we prove this is true even without this condition? So what's going on, sir? Why do we need fa equals fb?
Because otherwise it could just, the first derivative could just be positive or negative or continue in one direction.
I see. So you are saying that if without fa equals fb, you could have a picture like this. Something that keeps it going up. Then